Alright, so in this video I'm gonna be explaining another important paper with the title FOSR, First Order Spectral Rewiring for Addressing Oversquashing in GNNs. This ICLR paper in 2023. Graph neural networks are able to leverage the structure of graph data by passing messages along the edges of the graph. While this allows GNNs to learn features depending on the graph structure, for certain graph topologies it leads to inefficient information propagation and a problem known as oversquashing. This has recently been linked with the curvature and spectral gap of the graph. On the other hand, adding edges to message passing can lead to increasing similar node representations and a problem known as oversmoothing. We propose a computationally efficient algorithm that prevents oversquashing by systematically adding edges to the graph based on spectral expansion. We combine this with relational architecture, which lets GNN preserve the original graph structure and provably prevents oversmoothing. So a common approach to addressing oversquashing is to rewire the input graph, making changes to its edges so that it has fewer structural bottlenecks. So we have a graph and we propose fundamentally relies on relational GNNs. So we reviewed their formulation here. We define the general relational GNN layer by this, where psi here are message passing functions. And U is those neighbors that have particular relation over all relations. So this is the relational version of graph neural network. As a special case of relational graph neural network, RGCN layer are defined by the update, where sigma is a nonlinear activation. One can interpret the WH term as adding self-loops to the original graph and encoding these self-loops as their own relation. So we call it relational rewiring. We incorporate relations into our architecture in the following way. Suppose that we rewire G by adding edges, yielding a rewired graph G prime that has added edges, and we equip it with a relational structure by assigning each edge the edge type 1 and each edge in E2 edge type 2, for example in RGCN. So we can decouple these edges in edges 2, edges 1. So the original layer would include only the first two terms. A rewired graph with no relational structure would add the third term but use the same weights. A relational structure serves to provide the GNN with more flexibility since it remembers both the original structure of the graph and the rewired structure. So in this section, we analyze the smoothing effects of repeatedly applying RGCN layers with rewiring. Define Dirichlet energy. This is a not new one. This is an old idea, Dirichlet energy. And we define the rate of smoothing. And then they have the theorem So in order to use the RGCN framework, we need to make a choice of rewiring algorithm that is capable of adding edges without removing any. We propose a first-order spectral rewiring algorithm with the goal of improving graph connectivity. The rate of spectral expansion, for example, the rate at which the spectral gap improves as a function of rewiring iterations, is one of the key determinants of the oversquashing. Our algorithm follows a similar philosophy as it is referenced, optimizing the spectral gap of the input graph by sequentially adding edges such that the rate of spectral expansion is maximized.